Our next demonstration will be given by Dr. Marcus Novak, founder and president of NOVAA Ltd. The topic of demonstration is anti-jam, anti-spoof, and multipath resilient GPS antenna. The company will have 20 minutes to demonstrate their technology, followed by a 10-minute Q&A session. And when you're ready, we will begin. When you're ready to begin, we'll start the clock.
Okay, great. Yeah, let's do it. Hey everyone, thanks for coming out, thanks for sticking with us. Again, I'm Marcus Novak, and I'm really excited to share with you what we've been up to for the past 6 months. So I'm going to dive right into it here. What we're here to talk about today is GPS-based assured positioning, navigation, and timing. And what we're going to be demonstrating here in a few minutes is, I think, a very new and pretty significant capability for anti-jamming and anti-spoofing in an incredibly low size and low cost platform and applications. So this is approximately the size we're looking at here. As you'll see kind of as we go through, this is actually primarily a software-based technique, which makes it extremely scalable and extremely compact. So I think as we're all pretty well aware, GPS is a very pervasive capability. It's something that's touches upon virtually all our Army combat systems. This is something that's essentially intertwined in that sense with all 5 of the Army modernization priorities. And this is a topic that the Army is already spending billions of dollars on. And so the reason for that spending is because our widespread use of GPS at the same time becomes a reliance on GPS, and so we're vulnerable to adversary interference or manipulation of those GPS resources. And so here specifically today we're going to be talking about jamming and spoofing. So as you're probably aware, jamming is essentially just a denial of service. So this is when they simply overpower these signals which are normally coming from space and are very weak. On the other hand, spoofing is the more sort of sophisticated threat. This would be when the adversary is intentionally manipulating or sending false GPS signals towards our receiver to try to manipulate where we think we are. So the underlying issue here is really that the technologies that have been developed to date to try to address these problems are very much focused on some of our largest, more high-end systems. And sort of as a result of that, the solutions they come up with are likewise very high cost, generally larger size. Meanwhile, at the other end of the spectrum, we have this truly massive volume of low size, low cost, oftentimes expendable or single use type systems, which are equally reliant on GPS and need an anti-jamming, anti-spoofing solution in order to have any level of functionality in a modern conflict. And so this is really the exact feedback we got from Army stakeholders. Actually 6 months ago here at Global Force, that was unintended. So 6 months, sorry, we don't need the network, it just interrupted. So 6 months ago at Global Force in Alabama, we had the opportunity to talk with the PNT cross-functional team. And essentially they told us that same thing, right? They told us, and everyone there, that they want to attempt to tackle the APNT problem for the most challenging platforms first. They figure if they can solve that, then they can translate that to other platforms thereafter. And to them, their example was artillery shells. The guidance kit for an artillery shell is extremely low size. It's going to have to be a very low cost solution. And so it needs anti-jamming and anti-spoofing, as I mentioned. And so we really took inspiration from that, actually, and somewhat adapted the approach we had been proposing 6 months ago to really hone in on and target exactly that application case. So to take a look very briefly here at sort of the gold standard of anti-jamming today is something called a SERPA, or a controlled radiation pattern antenna. So these look something like this. It's a multi-antenna system, right? You'll have between 4 and 7 GPS antennas on board. And kind of the basic takeaway that I want you to get from this is that the way they function is what we would call vulnerable by default. So the functionality of this adaptive nulling technique that they use is essentially to attempt to let in all the signals coming from their entire field of view, and only then cast a narrow null or kind of a small region of rejection where they think the jammer is. So again, they let everything in and then block the jammers only. The approach we're doing is called beamforming. It's in essence the exact opposite. So we start by rejecting everything, and only then do we let in a narrow region of signals, which corresponds to where the physical satellite is in space. And so the benefit there is that we're protected from the unknown, namely things like spoofers, multipath, or even larger numbers of small jammers. We're protected by them by default, again, because we're only sensitive to the exact narrow piece of sky where the satellite is. And so we didn't invent beamforming in and of itself. It's a well-known technique, but the challenge here is achieving that high resolution in order to get that pinprick of sensitivity only to the satellite. And so normally that would correspond to a physically large aperture. You would need lots and lots of antennas to accomplish that. But what we've done here is take inspiration from the synthetic aperture radar community, who have for decades now been using a technique called synthetic aperture, whereby instead of having a large physical antenna, you can leverage the motion of the platform in order to synthesize a large virtual antenna. And so we essentially are adapting that same technique and applying it to other low size but moving platforms, such as, for instance, an artillery shell, anything along those lines. So in terms of the demo here, obviously we want to emulate as best we can that sort of use case, in this case an artillery shell or a missile or a bomb or something along those lines. And the key success criteria here for us are to realize high-resolution beamforming, and as a result of that, demonstrate anti-jamming, anti-spoofing performance. And we want to validate that this thing is going to work at relatively high velocity like we would see on these sort of platforms. So unfortunately, we couldn't get access to a howitzer for this, but we make do with what we can. So we tapped into the amateur rocketry community. And so for reference, this is, I think, a liquid-fueled rocket. It's about 8 feet tall, pretty serious thing that they launched out in the Mojave Desert. Approximately what we're setting up on this platform is a software-defined GPS receiver. So typically what you see there on the left, a more typical GPS receiver implements all the sort of acquisition and tracking loops in hardware. We push that into the software to give us some flexibility to experiment with new algorithms for that part of the process. And so that's what that payload looks like. Again, really nothing terribly special about the hardware here. This is essentially a breadboard prototype. These are off-the-shelf components we kind of plugged together. It's only running in the civilian band in this case, which makes it actually, in a sense, all the more impressive with the results we're about to see. Got some audio in there. As you can tell, that's the actual launch of the payload here. So that's nice. Pretty cool. So what we get here, and the key thing I want to point out here, is that coming out of the hardware payload itself, it's just an RF recorder. It's not actually doing the processing on board at this stage. So the raw signal capture here is not inherently meaningful. We're not sort of pre-processing this in any way. We implement all of that in the software loop then. And that's for the reason that we can then later inject these jamming and spoofing signals. So you see the raw signal capture approximately, and then the yellow trace there is the actual trajectory of that rocket. I believe it hit about 800 or 900 miles per hour, 4 kilometers altitude there. And so a good way to look at the performance here, and this is just essentially a pretty stock unmodified GPS receiver software. As a baseline, we can look at this acquisition and tracking performance, and we can see there's 5 satellites in view that day. Those are the 5 green bars. And it's able to acquire and track those, which we would expect. When we implement the synthetic aperture technique, we can see immediately that we have a significant increase in the tracking margin, the acquisition margin, because we're getting a much stronger signal because we're doing this beamforming. So to kind of see what the receiver sees in this case, if any of you are familiar with phased arrays or antennas, this is the actual beam pattern. So that spike you see off to the right is the location of the satellite in the sky. We're filtering for a single channel here. And you can see signals coming from any other direction get suppressed a significant amount. And the size of our synthetic aperture here, again, is 150 meters. So this is actually equivalent to having the performance of a 150 meter across phased array, and coming from a single antenna ultimately. So obviously, one thing we care about pretty immediately is what happens when we attempt to jam this thing. So as a simple case here, we're looking at a pretty low power basic randomly modulated jammer. This is the type of thing you can buy on the internet. It's a privacy jammer, as they call it. Now, obviously, we couldn't actually go jam the middle of California, but because this is a software-defined system, what we can do is inject this jamming signal before the GPS processing happens. So essentially, to our algorithm, it looks identical to as if this jamming signal came in directly through the antenna. There's really no difference there. So again, looking at this baseline typical off-the-shelf receiver, obviously it immediately gets jammed. It can't see any of the satellites because it's overwhelmed by that jamming signal. When we implement the synthetic aperture technique, we can again reacquire all of those satellites, again, because we have this ability to form a beam to each satellite individually and therefore suppress that jamming signal. So if we look at maybe a slightly more extreme example here, we're considering 10 jammers distributed about the battlefield. And this is actually a scenario that was brought to us directly from the Army Futures Command Missile Systems Group, because their concern was that SERPAs generally are limited in the number of jammers they can address. It's correlated to the number of antennas on the SERPA, so between 3 and 6 jammers. In this case, we have 10 jammers, individually, relatively low power, but between all of that, actually, a typical SERPA would fail under those conditions for that reason. Not because it's such a high-power jammer, but because there's so many of them, it overwhelms the spatial nulling technique. And so here we can see that when we implement the synthetic aperture technique, despite having 10 jammers on the field, we can still receive successfully those satellite signals. Obviously, we're impacted a little bit as compared to the single jammer case, but we're still having actually quite high margin to acquire and track these signals. So then the next case we kind of want to look into here is the issue of spoofing. So again, this is an adversary sending false satellite signals at our receiver. You can sort of see that on the diagram, the purple line pointing up at our point on the trajectory. It's sending the same satellites that are in the sky, but a false version of those. And so again, the baseline receiver here locks onto that fake spoofing signal. It can't differentiate from the true and fake signals, and it so locks onto that and thinks that's that. As you might come to expect by this point, when we do the synthetic aperture technique, again, we have the spatial resolution to distinguish those two signals and lock onto the true satellite signals. And so this is what that looks like under the hood. Again, we see two spikes in the field of view here. One of those is the true satellite signal, and the other is the spoofer. We know where the satellite is supposed to be, and we have a rough idea of where we are, so we know which of those is the true signal. And I want to point out, it's not an issue of which signal is stronger, right? The spoofer is actually stronger than the satellite signal in this case. The key thing is that we see two spikes. That means we can differentiate them, and we can essentially choose which signal to look at. Beyond that, that spike in the chart there corresponds to a real physical location. So what that means is if we look at 3 different satellite channels here, the 3 satellites, as we would expect, are coming from different directions, right? Because they're 3 separate satellites in the sky. Whereas a spoofer, if they're spoofing on multiple satellite channels, is still one physical device in one physical location. And so we see that one spike on the left-hand side is always in the same location. And so that's actually a giant red flag for us to say, hey, this is probably a spoofer and not, multipath or something like that. So to briefly recap on that, again, our goals here were to demonstrate beamforming from a single antenna on a moving platform at high velocity, and to demonstrate anti-jamming and anti-spoofing on those signals. And we succeeded in doing that. So what that means here in terms of operational impact, sort of on day 1, is that when implemented, your guided munitions, hit the targets you expect them to. Right, and that sounds sort of kind of trite and maybe simplistic, but it's obviously simplifying a more complex scenario. The CSBA actually did a case study on this subject and essentially found that if you're not accounting for these electronic warfare conditions on the modern battlefield, you'll end up needing the reduced sort of probability of hitting your target with the munitions results actually in a 5 times increase in the number of resources needed to accomplish the same mission. Moving outward from there, of course, the broader impact touches essentially anything that touches GPS, right? Obviously, we've been focusing a little bit on the guided munitions component, but there's some obvious parallels to loitering munitions, moving from there into UAS, swarming applications, truly all other low-size, low-cost type platforms. And there's even, of course, the benefit of hybridization, where you can combine these benefits with the strengths of a SERPA, for instance. It's not a one or the other type issue. And of course, we see these same issues on the commercial side. They're driven largely by autonomy applications, things like self-driving cars and drone delivery and other such applications. These are all obviously very reliant on GPS as well. And likewise, they only have access to the civilian signal here. And so these, again, we can address those same issues using the same technique here. In terms of starting to look towards transition, we benefit from the fact here that this is based on very mature technologies, really. The scientific underpinnings, again, comes from the SAR field, which has been in use for decades at this stage by the military and others. And likewise, we benefit a lot from modern solid-state RF electronics and high-speed digital electronics, which have come about in the past 20 years or so. And likewise, the maturity in the military, especially of software-defined radios, FPGA-based systems, that I think will be a huge benefit in translating this to the field rapidly. I'm not going to dwell too much on the actual transition plan here. The key thing really is that we recognize we need partners to carry this out. We need partners in industry and within the Army to find the appropriate acquisition vehicles and platforms and integration activities, and that's a large part of what we're trying to accomplish here at AUSA. And so the core team, again, includes myself, obviously, on the technical side, as well as Rob Russell, who will be joining us for questions. And really just the key takeaway here is we have core expertise in the important fields of this area, both technically and in the military and on the business sides. So with that, I think we flew through this in pretty good time, but I wanted to make sure we have plenty of time to address any questions you guys might have.
First of all, thank you. You make it sound very easy and understandable.
Oh, sure. Well, I'm glad.
Not being very knowledgeable about synthetic aperture techniques, do you need a fixed model for the kinematics of your moving vehicle? Does it make certain assumptions about the velocity and time?
You don't per se need fixed knowledge of the application. What you do need is a relative time scale position estimate. So that means you would want to, for instance, integrate this with something like an IMU. You need to be able to know, in a rough sense, where has the platform moved from where it was in the past 100 milliseconds. So short-term accuracy, things like an accelerometer are very good at that.
So would controlled maneuver add a complication to this? That's what I was getting at.
Sure. Not terribly so, I think. Controlled maneuvers, if you have input from the system doing the maneuvering, that helps. Also, likewise, you would detect that, again, on the millisecond time scale from your other sensors. So for instance, even in this launch we did, right, the rocket is accelerating for several seconds. And if we just assumed a linear velocity type trajectory, it wouldn't have worked. We had to actually compensate for acceleration.
So that was your model, effectively.
Exactly, yeah. Yep.
A couple of questions.
Sure.
Do you think what's the more technically challenging problem to solve, the spoofing or the jamming aspect?
So in a sense, it's interesting in that they both. You don't really have to differentiate from them very much because they both essentially get solved at the same time. When you're doing beam forming instead of null forming, you kind of get both immediately. Yeah.
You get the integrity as well as the.
Right.
Yeah. And with the multiple jammer, is there a fundamental physical limit to the number of jammers that your technique can overcome?
No, your limitation comes from the combined power at the receiver. That's kind of always going to be a limit with jamming. The only other limitation would be if they intercept your line of sight to a satellite. And in that case, you would lose that one satellite, right? But you would still maintain all the other ones. So essentially, to deny you service under this sort of paradigm, you would have to simultaneously intercept line of sight to all your satellites at once, which is challenging, at least.
And did your model assume that going in, you knew where the 5 satellites were pre-stationed prior to being spoofed or jammed?
Yeah, so typically, again, it's high resolution from a beamforming standpoint, but in terms of, kind of the ephemeris of the satellite constellation, it doesn't have to be within, a meter. We just have to know it's within a degree of this position in the sky, which is public knowledge already. Mm-hmm. And we can, of course, even if we don't know, if we want to find them from scratch, we can do a search, essentially, and just say, what do we see? Yep.
Does it work for other GPS systems, other countries' GPS transmitting satellites?
Sure, yeah, and so there's no inherent limitation in terms of what frequency you apply this at, what constellation, what network. Obviously, our demonstration here was we did all of this just using the civilian code on L1, but you could do this on multiple frequencies simultaneously. You could do it on GLONASS, Baidu, whatever you want. Mm-hmm.
You did all your jamming software-based, right? Any plan to do an actual physical test of jamming? So old school people like
yeah, I
myself,
mean, absolutely. That's something we'd love to do, and that's obviously in the coming stages. We've been invited to several of these sort of jamming events, NavFest and similar, where they pull out the jammers and actually shut down the airspace. And that's something we'd have to prepare for a little bit, just because with the synthetic aperture technique, we do need a moving platform, so we can't just drop a receiver in the field and let them have it. It needs to be, we'd have to fly a drone or something along those lines. But that's absolutely planned, yes.
Artillery projectiles, hundreds of meters per second. Drones, not so fast.
Mm-hmm, sure.
Does it change your processing time, or just make the calculations tougher? Or
yeah,
what kind of differences?
That's a really great question. And so when we set out to do this, and part of why we launched on a rocket and we're targeting artillery initially, was we had thought it would require actually that high a velocity. But looking through the data, it's going to keep happening. Looking through the data, and actually kind of if we look at the data set as the rocket approaches apogee and starts slowing down, we came to realize actually the technique works quite well at lower velocities as well, right? Tens of meters per second, that's easily a drone, a small drone flying. And actually, really, we didn't set out to solve the problem of a dismounted soldier, but in that case, obviously they're not moving even at tens of meters per second. But what we found there, or what we think will happen, is that instead of just the speed of the platform, we can essentially use the complexity of the movement of something like a dismounted soldier to realize essentially the same benefit. So that's something we're looking into in the future as well.
So for a vehicle,
Mm-hmm.
ground vehicle, tens of meters still might be able to have the synthetic aperture.
Yeah. Mm-hmm. Yeah, that's what the data is indicating. And that's why we're, for instance, we have good interest on the commercial side, where if you have a car that's driving, even in an urban environment where you're dealing with multipath, this could resolve that issue as well.
How small of a size do you need for that aperture? I mean, you're saying the larger thing will give you, a larger attenuation, but how small can we go with it?
Yeah, and there's two parts to that question, really. One is that, as we said earlier, you can do this at lower velocities, right? And lower velocities sort of implies a smaller aperture. Again, physically, it's a single antenna anyway. But in terms of the virtual aperture, you can just essentially start integrating over a longer time period to realize that same very large, high-resolution aperture.
So with the software approach, what's the timeline for detecting, oh, I am being spoofed or I am being jammed? as opposed to being able to, once you do that, the next step would be some kind of tactical
Sure.
response.
Yeah. Mhm.
Yeah, how you-
Yeah, and that to a large extent that depends on the final implementation if you want to optimize for that or not. But certainly it should be realizable within milliseconds time scales.
The cost advantage, you said SERPAs were very expensive.
Mhm.
Your solution, the software-defined radio,
Yeah, so the real cost advantage,
are 100?
I mean, if we ballpark a SERPA at costing 20,000 plus, right? There's no reason to believe that at a certain scale you couldn't implement essentially a software plugin for hundreds to under $1,000 certainly. So, yeah, I think there's a significant opportunity for very low cost implementation. Because essentially you're assuming that this platform already has a GPS receiver, which presumably it does. So all you're doing is really updating the algorithms.
So what are the challenges with a software-based approach as opposed to having some physical mechanism you use to detect a jam or a spoofer?
Yeah, honestly, in a large sense, there already exist a lot of software-defined GPS receivers in the field. So the software-defined aspect, I don't think is a significant limitation, largely because we can leverage, again, the maturity of DSPs and FPGAs to where in the past that really wasn't feasible. You couldn't get enough general computing power to do it. Nowadays, we have access to that. So I don't think there's a strong limitation there. Anything else? All right, well, thank you guys again for taking the time and sticking with us. And yeah, I hope to talk with you guys throughout the week then. Thank you.